Gaussian's going to finish it off. Thank you.
Okay, thank you. Okay, so I'm going to talk today about some Gaussian process methods for large and high-dimensional data sets, and this is work that I've done with Zubin during my PhD. It's some of it, some of you may have seen before. Some of it's a few years old, but hopefully there's a little bit of a new spin on some of it too. So the problem is a very well studied task, that of nonlinear regression, and so in particular we have some noisy data, and we want to learn some sort of nonlinear regression function through the data, but importantly we also want to learn some reasonable error bars and uncertainties to go with that. So for example, we want to represent the noise in the data, but also reflect perhaps that as we move further away from data, we're less certain about the regression function. Gaussian process is a really quite an elegant way of doing this type of nonlinear regression, because it allows you to directly specify a Bayesian prior over functions, and then in conjunction with some sort of noise model or measurement process, you can then learn full posterior distributions over functions, and so get these kind of nice error bars. So during this talk, I'm going to use lots of simple 1D examples like this, but they're really just for illustration, and take them with a bit of pinch of salt. I'm generally meaning some sort of reasonably high-dimensional input feature mapping to some sort of regression output variable. So what is a Gaussian process prior? Well, it's a consistent Gaussian distribution on any set of function values, which are called f, given some set of corresponding input features. So for example here, I've drawn one function draw from a Gaussian process prior with, here I've represented capital N function values from that process. So what is the Gaussian distribution that's used? Well, it's a zero mean multivariate Gaussian distribution. Zero mean is just used by standard, it doesn't have to be. But the important thing is the covariance matrix, and that's I've represented in color here, with magenta being high covariance and cyan being low covariance. So this covariance matrix is the important part, which tells you about the correlations in the functions and gives you the sort of prior smoothness properties. So the way this covariance matrix is constructed is from a covariance function, which tells you for any two function values, it tells you how they're correlated. For example, you might use a covariance function like this, which is a Gaussian covariance function, which just says that correlations drop off as 2 points become increasingly separated. And that generates this type of covariance matrix and gives you very smooth functions. But there are many other choices there. Typically, they're governed by a small set of hyperparameters. For example, here we have a length scale for each of the input features 1 to D. To actually do Gaussian process regression, once you've defined the prior, we need a noise model. Now, I'm going to just talk about, in this talk, about a very simple noise model, which is just a Gaussian white noise around the underlying function. But with extra machinery, you can also think of more complicated distributions here. And the Gaussian process predictive distribution tells you what's your mean prediction and what are your error bars. For example, suppose I want to predict at a point x star. The blue line here is the mean prediction, and these are two standard deviation error bars, the red lines. And they're just given by some closed form matrix equations. So this is all very nice, but for machine learning tasks at least, one of the main problems is computation, which has a rather bad scaling with the number of training data points. So for training, it's n cubed, because of inversion of the covariance matrix. And for prediction, it's n squared per prediction point. Notice the scaling with the dimensions is not too bad. It's linear in this case, and that just corresponds to actually constructing this covariance matrix by summing over the dimensions. Okay, so sparse Gaussian processes. Well, first of all, where does the n cubed computation cost come from? Well, it comes from the fact that Gaussian process is a non-parametric model. Similar to some of the models Zubin was talking about earlier, the function complexity naturally increases as you get more and more data, which is a very nice property from a Bayesian point of view. And this non-parametric process naturally generates full rank covariance matrices. So this covariance matrix here is full rank, rank n, and can't be simply represented by just some sort of small finite basis. However, to try and actually speed these things up, make them more usable in, say, real-time systems in machine learning tasks, people have made many different sparse Gaussian process approximations. And generally, they're related and have a similar idea. I've mentioned a few authors that have worked on them as well as us. And they're based on projecting to some kind of low rank approximations, or in other words, projecting on some sort of small basis. And in doing so, suppose you project on a basis of size m, then you can reduce the cost to order nm squared for training, order m squared for prediction per test point. But if you're not careful when you do this, you can actually mess up some of the nice properties of the Gaussian processes that you started with. So I'm going to talk about a particular approximation that I worked on, which we call the sparse pseudo-input Gaussian process. To derive this, I'm going to just first talk about a particular generative view of a Gaussian process prior. And that's a two-stage sampling process. So the idea is you pick some small set of m we call pseudo-inputs, because they don't have to be real data inputs. They're just parameters. They live in the same space, but they're just prototype points, effectively, prototype input points. Draw the small set of corresponding function values from the Gaussian process prior, and then conditioning on as if we'd observed these, we draw the rest of the function. So this would be one sample drawn from the Gaussian process. Here's the conditional distribution, or at least this is the conditional covariance matrix for this particular positioning of pseudo-input. So we see that there's two gaps here in the correlation where we've already observed these points here. There's no covariance left, and then there's some growing covariance in the middle and at the outside to generate the rest of this function. Now, so far, this is exactly the same as if we'd drawn this function from the original Gaussian process prior. So we just separated it into two stages. But we can make a factorized approximation to that conditional distribution. So we approximate it by the product of all the point-wise marginals. And once we've integrated out over the unknown latent, the small set of unknown latent function variables, we obtain an approximate Gaussian process prior, which we call sparse pseudo-input Gaussian process, but it's also been called by others since then the FITSI, which stands for fully independent training conditional approximation. Now, the important point about this prior is really summarized, rather than looking at equations, you can sort of summarize it in this picture here. This was the original full rank covariance matrix. The approximation actually looks like this, and it's made up of a very low rank part. So these are just very thin rectangular matrices here. They're these covariance matrices correspond to the covariance between all the training inputs, and just the very small basis set that we've chosen. So there's nothing too new in this part. This is a low rank projection, but this part turns out to be quite important, and this is a diagonal correction, if you like. So it adds along the diagonal such that just along the diagonal the approximation is exact to the original Gaussian process. And because this is only a diagonal correction, the costs are, as I explained earlier, order nm squared for training. Now so I just want to say a few things about this type of approximation to do with sparsity and correlation. Well, this type of model is in essence a sparse finite basis linear model, but it has a few special properties. It has regions of decorrelation that allow us to reduce computation from the original Gaussian process, which just has full correlation everywhere over all space, whilst maintaining uncertainty in the process, but just purely in the form of variance rather than covariance. So what you're doing in essence is sacrificing correlations in some areas where they are hopefully not needed to represent your data. So if you look at this as a prior for functions, it looks very strange. This here is a single draw from this Gaussian process approximate prior, and what you get is you get pieces where you get some smooth function as before, but then it fades into areas where you get decorrelated noise. So it's weird to have, if you like, a noise process as part of the prior, but it's a sort of necessary trade-off in this case to reduce the computation. Now, of course, you have to ensure that you can get the bits where you need to model correlations in the right places with respect to your data. And for that, we have a particular training method or optimization method that is just a likelihood, it's a maximum likelihood method by gradient descent. So suppose we have some data set here and we choose initially some set of pseudo inputs that are all bunched in the middle, and also have actually drawn here the hyperparameters of the covariance, which are here. The amplitude of the process is too big, the length scale is too long, and the noise is too small. And the prediction as it stands, you can see represented with these black and grey lines. And after optimization, these pseudo inputs move along and spread themselves along the data to better model the data. And the hyperparameters adjust themselves now to have a reasonable length scale and a reasonable amplitude. And the final prediction looks extremely similar to the original Gaussian process prediction would for this data set. Has the naturally growing error bars that we want, but is just represented by this small set of pseudo inputs. So the cost is dramatically reduced from the full GP on this data set. So this is just 1D for illustration. I'll show you some results on some more realistic data sets later on. So this is one way to go if you want to speed up Gaussian processes. But there's another sort of direction, which is again an old line of thought, which is to do a much more of a local regression type approach. So this FITSI approximation I've been describing can really be thought of as a global approximation in the sense that it has a small basis set, m pseudo inputs, but they summarize all n data points globally. And as we said before, that it has a training cost of nm squared and a prediction cost of m squared per test point. But with certain types of data sets, even this is not really enough, because what you end up needing for very complex data is a very large M. So you need to cover the space very densely with lots of basis points everywhere. And since the covariance function that we're using in Gaussian processes is often some kind of local covariance, then maybe just a local approximation would be better. So as a sort of straw man, what I mean by this is, suppose you do the very basic thing of just clustering the data set into blocks, local blocks, using some sort of cheap clustering method, and you use independent local GPs that are not connected to each other at all on these blocks. Now, if you divide it into equal block size B, then the training cost will be NB squared for the full data set, and prediction cost per test case, once you've assigned a test point to a single block, is order B squared. So if you like, these things can be sort of directly compared. B, in some sense, can be considered similar to the role that M plays. So I just have some really simple 1D illustrations that hopefully give you an idea of the type of data sets that might be better represented by one or the other type of approximation. So here's an example which is really nicely represented by the Fitzy approximation with a very small number, regularly spaced pseudo inputs that summarize very smoothly and nicely this data set, because it has a long length scale, a smoothly varying data. But suppose we have some much more complex data that really does have a short sort of length scale that you need to model well. Well, if you just stick with the same number of pseudo inputs, then it really doesn't do a very good job. That in between each pseudo input, the variance just grows because it can't model the correlations in those regions at all. Whereas, if you tried a local regression approach, and this is the crudest of local regression approaches, where we just divide the data into blocks, so they're denoted by the alternating colors here, and at test time we just assign a test point to its nearest block, and we use a local GP regressor. So okay, I have all these ugly discontinuities which could be smoothed up in some way, but the main thing I want to say is that actually, if you were to look at some sort of squared error measure or a probabilistic error measure, this would actually get a much better result than the previous one here. And it has the same cost. If you ignore the clustering cost for now, it has the same cost as this, because there are the same number of pseudo inputs here as there are points in each of these blocks. So when doing a sort of regression, I think you need to consider which sort of regime your data might be in. And when we get into more high dimensions, in fact, these local type approaches work less well, and the more global Fitzy type approach actually works better in higher dimensions. I'll skip that for the moment. So one thing we thought was, is there a neat way to combine both of these types of approximation into a single one? And there is actually a really quite neat, elegant way of doing that in the same framework, the same approximation framework. And all you have to do is replace, so in the original approximation, I said we approximated this full conditional distribution by a completely factorized one. And that gave us this diagonal correction matrix, which made sure that the approximation was exact just on the diagonal. If we replace that with not a complete factorization, but a block factorization, a local block factorization, then the correction is a block correction, block diagonal correction. And we get a little bit closer to the original GP prior. And in fact, so this approximation is now exact on the blocks. But it also has an underlying low rank component to it, given by the pseudo inputs as before. And I won't go into the details of the sort of how you calculate the predictive distribution for this approximation and the costs, but it's essentially very comparable. So we did a bunch of experiments on some really standard regression data sets that have been sort of well tried and tested, at least for Gaussian process modeling, measuring test error versus computation time. For the FITSI approximation I talked about, a purely local GP type local regression approach and the combined approximation that I just mentioned. And in each of these, we vary the number of pseudo inputs we're using, or the number of blocks we're using for the local regression, or both for the combined. So as we vary them, we get different computation times and we get different error rates, and we look at the curves. The pseudo inputs are optimized as I described before, and the blocks are just chosen by some cheap clustering method. So these data sets have sort of moderate dimension size. These ones aren't particularly high dimensional. I'll talk about some high dimensional ones in a moment. And some of these are reasonably large in size. So we get some interesting things. So this Sarkos data set is actually a sort of very highly nonlinear data set. And it turns out that it's by far and away better to do a local GP, or in fact the combined approximation that I just showed, approach than it is to do the FITSI approach. So this here is an error measure. It's a probabilistic error measure. It's the negative log predictive density at the data. And this is computation time. And you see that basically it just saturates with it. You can essentially do a very local regression using a fairly small block size. The neighboring points determine the regression actually much better than using some sort of global regression that takes into account of correlations across the whole data set. But we get the opposite sort of approach for this data set abalone, which is actually I think a much smoother data set. You can actually represent it extremely well with a very small number of pseudo inputs. It has some sort of broad general trends to it that you can pick up, and that is much faster than using a local type approach. And yeah. It does worse in this case because there's a little bit of overhead to doing the combined thing compared to just doing a pure local thing, and that hurts you a bit in terms of time. So yeah. Oh, okay. So what exactly are you saying? So that it does get slightly better error than the purely local, but costs you a bit.
No, I thought
yeah.
FITSI is an extension of the FITS is an extension of the FITSI.
I'm sorry. Yeah, I'm sorry. Yeah. So there's some other curious effects going on here, which are that, in fact, I've been telling you all this as if we're sort of trying to get as close as we can to the original Gaussian process with its stationary covariance function. Now, actually, the FITSI approximation is more flexible than that in some sense, because it can move its pseudo inputs around. And if the original covariance function actually wasn't a brilliant fit, it can turn out that the FITSI approximation can end up being a better model for the data. The local one, the combination with the FITSI and the local is closer to the original GP, but it's actually a more constrained model from that point of view.
Full GP would do worse as well.
Yeah, the full GP would do does do worse here, in fact. So there's some other complications going on here, but this data set's maybe not brilliant, but it does illustrate that in some cases you can summarize a data set very, very well with a small number of pseudo inputs, and that can be very, very fast compared to some other approaches. And the final one, the combined approach, does a little bit better than either of the other two. We never really saw any big wins for the combined approach. It either seemed to be the case that a data set is well represented by a local regression or well represented by the global type regression, and not so many in between. But this is an example of where we can get a little bit better by using the combined approach. Okay, I'll quickly talk about higher dimensional data sets. So actually, GPs scale well with the number of dimensions in the sense that for a typical covariance function, it's just linear. But however, with the FITSI kind of approach, where you're actually searching for the positions of these pseudo inputs, it becomes a problem because we're searching in a high dimensional space, and that becomes unfeasible when you have very large number of dimensions and say a large number of pseudo inputs. So one thing that we do is we use a very simple linear projection to a lower dimensional space, such that these pseudo inputs can live in a small dimensional space, and the optimization can take place in that smaller dimensional space. So it's sort of like doing something like a PCA, but it's a supervised version of that where the projection is learnt at the same time as in the same optimization. So maybe I'll just skim over the details, but here's an example where we have a 106 dimensional space. We actually use this in a modeling competition, and the original sparse GP method that I talked about, this is the FITSI or the SPGP method I talked about, gets very good error rate for this particular data, but the training time in particular is quite high. But if we project down to in this case just five dimensions, and we learn that linear projection, we get very comparable error rates with a much reduced training and test cost. And just for sort of comparison, if you did just do a PCA pre-processing and then did a Gaussian process on top of that, you don't do nearly as well. And we did actually use this to win this particular competition, or this data set. So just to conclude, with some of these methods, I think it is possible to apply Gaussian processes successfully to large and high dimensional data sets. Maybe the work maybe hasn't been done to really scale them up to super big data sets, millions of points and thousands of dimensions. So I think more methods are needed there. The type of approach I've talked about are two types of approaches. One is the FITSI approach, which basically sacrifices correlation to reduce computation, but it still maintains sensible predictive uncertainties. And the other is a local regression type approach, which actually can perform very well for some data sets. So it's important to identify which regime you're in to know which method to use. But I think further sort of theoretical analysis and experimental analysis is needed to actually sort of do this and to know in which exact regimes, in terms of length scales of your data, in terms of sample density of your points, which regimes these particular different methods work best. So yeah, thanks very much. Yeah.
There's some comment for your, model selection problem.
Yeah.
Do you just simply say use a PCA? So actually, when you use a PCA, you didn't consider the relationship between those Y and X.
Yeah, that's right. Yeah.
And as a recently, and as my current PhD student, he is also working on the model selection for the Gaussian process.
Yeah.
And he find that lasso works actually quite well.
Okay.
And for some problems, if those X have a higher correlated, if those X they are higher correlated.
Yeah.
And he find that elastic net actually works very well.
Okay.
And he also used those we used the so-called SCAD net, and also for the SCAD net it's unbiased.
Okay. Okay. Yeah. Yeah. I mean, the completely unsupervised PCA was in a way just a sort of very simple baseline test, and what we were doing is the very simple supervised linear projection within the Gaussian process framework, where we learn the projection within the same framework. But it could be good to test against some of these other methods too. Yeah. Thanks.
A very simple question. If
Yeah.
you're really in one dimension, you might use a cubic smoothing spline.
Sure. Yeah.
Does that generalize up?
Does that what?
Does
Sorry?
that generalize up to higher dimensions?
I mean, they're all very related, these methods. So I think these smoothing splines can be seen as even as a type of Gaussian process in some ways, where I believe where they're rather than specifying the covariance function, they can be seen as sort of specifying the inverse covariance function.
Well, the inverse is sparse, which speeds up your computations.
Yeah. I mean, the usual reason why we here want to specify the covariance rather than the inverse covariance is that gives you a consistent process which generalizes to new unseen points in a consistent way. So when you specify the inverse covariance, you sort of need to have your training data and the points you want to test on from the outset. If you add in different points at a later date, it changes the regression. When you specify a Gaussian process with the covariance function, it's automatically consistent so that as more data come in, it's not as if you'd go back and want to change the regression you made on the first data points. In other words, it has the marginalization property sort of works. So I think from that point of view, it's nice to have it this way around. But for examples where you do know ahead of time the places you want to evaluate, then the spline approach would be naturally computationally sparse. But I don't really know about splines in high dimensions, though. I'm not sure.
Pretty awful beyond 2 dimensions.
Yeah.
It doesn't really work.
Carl probably knows better than me, but although I've presented lots of results in 1D, I didn't really want to stress that. They're just sort of illustrative. The nice thing about this is it does work well in high dimensions, particularly the Fitzy approximation seems to still work pretty well in high dimensions. Yeah.
When I sample from this prior, I get this noise.
Yeah.
I'm not sure if I agree on that. I mean, that depends on how you define the sampling away from all the points that you basically pin down, right? Let's say the training and your pseudo inputs. And if you define the conditional distribution of all the others, given these guys,
right,
in the usual way, you wouldn't get that noise. I mean, I think this is Joachim came up with this. I'm not sure if I like it.
I can see why people don't like this.
If you just define it as usual, you get, I mean, this is just a smooth covariance function as any other. It's just a bit unusual. But
Yeah, I can see why people reject this plot. In fact, just when you use the Fitzy approximation, it doesn't mean that actually your predictions can't be fully correlated Gaussian process predictions. But I think this does, whether you want to call it a prior, maybe that's just semantics, but I think this does get to the heart of what is actually going on inside the approximation. You know, if this was your if this is the space you want to cover, it does show that you're having to sacrifice correlations in some areas of the training set in order to gain computational efficiency.
Yeah, but okay, so but this seems like a phase transition, right? From a smooth process prior that
Yep.
generates analytic functions.
Yep.
Even the sample paths are analytic functions
Yeah.
for the Gaussian prior to random noise. I mean, this is a complete phase. And I mean, it's only because, I mean, if you define it a bit different, you would have something that is still an analytic covariance function, but which is in fact unusual. Depending on where you put these pseudo inputs. I mean, it's,
Yeah. Okay. Yeah.
it looks crazy, right?
It certainly looks crazy, but you know, if you're interested in point-wise predictions, then at the end of the day, the predictions you get out of it are very reasonable and look totally smooth and just like a Gaussian process.
I mean, for example, if you take I give you 2 points, you should predict at 2 points that are
Yeah.
epsilon apart.
Yeah.
Wouldn't the correlation go to 1 even under your most strongest approximation? I mean, now you fix all your pseudo inputs and you fix anything that you can change.
Yeah.
And I just ask you about what is your guess about the correlation of 2 points that are epsilon far apart?
Right.
That should go to 1, right? And that is what I mean by a smooth
Yeah.
behavior. And so I mean, for random noise, it wouldn't go to 1. It would always be completely uncorrelated what you predict.
Right. Right. I guess. Yeah. I guess you do have to be a bit careful how you define it. And okay, rather than random noise, it's really this independence between the training data points that's the approximation. It's saying that they're conditionally independent. That's the approximation you're making. But by drawing that plot, I just wanted to sort of point out that when you make that conditional independence approximation, you are throwing out some of the correlations that were there in the original prior. So that's okay. Yeah.
Do you want to comment on possibly using these lower dimensional projections for doing ARD and determining which features are relevant? And I'm thinking of especially when your likelihood is non-Gaussian and it's really expensive to get gradients. The log Marshall likelihood. Is there any way to use your method to scale down your input space enough to make that cheaper cost?
Yeah, maybe. The problem is the method as it stands that we used is it partly makes it simpler because you're projecting to a low dimensional space, so you have to do this optimization. You're doing this search for pseudo inputs in small dimensional space, but the problem is to keep it smooth, we're learning a full projection matrix P, whereas if you started with the original ARD kernel, which is defined right at the beginning, which just has a single, say, length scale for each dimension, which you can use to sort of select features. This is like a fully sized P, a square P, square diagonal P, and we've changed to a thin but full P. So we still have quite a lot of parameters in that projection matrix. So it does do ARD in some sense, but it also mixes up all the dimensions altogether.
So in both cases, your X points stay in your high dimensional space, and you don't actually optimize them in some.
No, they are in the lower dimensional space. But you mix all the dimensions together when you project to get to that lower dimensional space. Linearly mix them.
But you could use ARD on top of that.
You could use ARD as well to select from those. Yeah. I don't know how you could smoothly use ARD without that sort of full P matrix and.
Regression.
Very
Yeah.
nice one, Dennis.
Do you find that the
But you can usually get very good approximations in low dimensions. In your award-winning example, you went from 106 to 5.
Yeah.
Do you find that that's a characteristic of a lot of examples you've worked upon, or is that was that sort of unique to that particular one?
That we could get away with this very small,
Very small dimension.
very small dimension. It wasn't unique to that one. I think that was probably there was a few other from that particular competition. There were some other data sets that we also used a projection method that I haven't shown the results for. This is probably the best one that we had. But no, I think it can be fairly typical partly because it is able to mix the dimensions together using that projection matrix. So it can pick out some sort of lower dimensional basis that is a reasonable representation of the regression function.
When you're searching over the projection matrix,
Yeah.
you're searching over a Grassmann manifold, and that doesn't take all that many parameters to specify. For a
Okay.
Grassmann manifold, you need D times P minus D parameters, and it doesn't seem to me like you're going to be increasing all that much over the diagonal that you were searching over.
Okay. I'm not sure about that. Maybe I can talk to you about that afterwards. We did a very naive thing of literally optimizing all those parameters, but that's perhaps unnecessary.
Yeah, that is
Yeah.
unnecessary. Yeah, okay.
Okay.
We can talk about that later.
Okay. Thanks.
Well, since Richard Sandworth has just turned up, it must be time for a drink. So, I'd like to thank everybody for a very interesting afternoon. And I think especially to Zubin and David Banks, who I think will help behind you. Good one it has been. So we hope you'll stay and have a drink with us upstairs.